This is a video for AQA Further Pure, Complex Numbers 4 De Moivre's Theorem, 4.5 Finding Multiple Angle Identities using De Moivre's Theorem. You should know this one here, cos squared plus sine squared is equal to 1, whatever the value of theta. You should know this one, although it is covered in the second year of mathematics, and you may not have met them yet, but we are going to use them nevertheless. The compound angle formulae, so this is the cos of the addition of two angles, can be rewritten in terms of the cos of each angle and the sine of each angle, and similarly with sine. You'll often see these written as cos of a plus b and sine of a plus b, but they are the same formulae. And the double angle formulae, sine 2 theta in terms of sine and cos, and cos 2 theta in terms of cos alone or sine alone, or indeed cos and sine. And this latter one, the cos 2 theta one, we'll see quite a lot when we're doing some integration work. Okay, here's our first example. We've been asked to use De Moivre's theorem to show that cos 4 theta can be expressed in terms of powers of cos and sine, and sine 4 theta can be expressed in terms of powers of cos and sine. This can be done without using complex numbers, but it is considerably easier to use complex numbers than not. Okay, so cos 4 theta and sine 4 theta, well, they feel like they've come from here. Cos 4 theta plus I sine 4 theta. We know from De Moivre's theorem that that's equal to cos theta plus I sine theta all to the power 4. And what I'm going to do is multiply out this right-hand side using the binomial theorem and Pascal's triangle. I know that for power 4, Pascal's triangle is going to give me 1, 4, 6, 4, 1 as my coefficients. So this thing is going to become cos to the power 4 theta plus 4 lots of cos cubed theta times I sine theta plus 6 lots of cos squared theta times I sine theta all squared plus 4 lots of cos theta times I sine theta all cubed plus I sine theta all to the power 4. So that's going to give me cos to the power 4 theta plus 4i cos cubed theta sine theta. And then I'm going to get I squared in here, and we know I squared is minus 1, so this is going to give me minus 6 cos squared theta sine squared theta. I cubed in here, so that's going to give me minus I, so this is minus 4i cos theta sine cubed theta. And finally I'm going to get an I to the 4, which is just 1, so I just get plus sine to the power 4 theta. Now I'm going to look at the real parts, and for the real parts I've got here cos 4 theta, and I've got here cos to the power 4 theta, a minus 6 cos squared sine squared, and a plus sine to the power 4. So I get cos 4 theta is equal to cos to the power 4 theta minus 6 cos squared theta sine squared theta plus sine to the power 4 theta. And for the imaginary parts, if I look at those, well, The coefficient of I on this side is just sine 4 theta, and the ones that involve I are here and here. So I'm going to get sine 4 theta is equal to coefficient of I here then is 4 cos cubed theta sine theta minus 4 cos theta sine cubed theta. And if you look at those two, those are the same as the expressions we've got up here. There's all of that written up for you. You can see here we've used de Moivre's theorem to give us an expression for cos 4 theta and sine 4 theta, multiplied through and then tidied up, equate the real parts here, equate the imaginary parts here, and we get the answers as required. Sometimes it's useful to be able to do the reverse, to be able to write something like cos cubed theta in terms of coses or sines of multiple angles. So we might be looking at cos 3 theta or cos theta. So sometimes we want to be able to do this kind of identity. So if we start out with z is equal to cos theta plus I sine theta, then z to the n gives me this, z to the minus n gives me this. So when I add them together, I get 2 lots of cos n theta. So if I divide that by 2, I will get that cos n theta is equal to z to the n plus z to the minus n over 2. If I take them away, those will go, and this will give me a 2i sine n theta. And so when I divide by 2i, I get this result, which is that sine n theta is the difference between z to the n and z to the minus n over 2i. Don't forget the 2i. Dropping the I is a very common mistake, so watch out for it. Okay, let's look at this example here. I want to get sine cubed. Where do I start? Well, I start by letting z equal cos theta plus I sine theta. And this is a common starting point. You'll see this over and over again with this type of problem. Sine theta is equal to z minus z to the minus 1 over 2i. That's using our formula from the previous slide. I've just got sine of 1 theta, so I get z to the 1 minus z to the minus 1 over 2i. Rearranging this, I'm going to get that 2i sine theta is equal to z minus z to the minus 1. Now I'm going to cube this whole thing, and you'll see why in a second. If I write 2i sine theta all cubed, I know I'm going to get something involving sine cubed, and I want an answer involving sine cubed. And that's going to be equal to z minus z to the minus 1 all cubed. This I'm going to multiply out using the binomial theorem again and Pascal's triangle, which is going to give me coefficients of 1, 3, 3, 1. And that's going to give me minus 8i sine cubed theta is equal to, I get minus 8i because 2i cubed is 8i cubed. I cubed is minus I. So minus 8i sine cubed theta is equal to z cubed plus 3z squared times, well, it's minus z to the minus 1 plus 3z times minus z to the minus 1 squared plus minus z to the minus 1 cubed. If we work that on through, then I'm going to get z cubed. I'm going to get minus 3z. And from here, I'm going to get plus 3z to the minus 1. And here I'm going to get minus z to the minus 3. And remember, that's still minus 8i sine cubed theta. Well, again, just rearranging this for a second, I get z cubed minus z to the minus 3. And then I'm going to get minus 3 lots of z minus z to the minus 1. And again, I've still got my left-hand side. Well, if we look at this, I know that z minus z to the minus 1 is 2i sine theta. And I know that z to the 3 minus z to the minus 3 is going to be 2i sine 3 theta. So I've got here 2i sine 3 theta minus 3 lots of 2i sine theta. So dividing through by my minus 8i, well, the minus sign is going to have the effect of reversing this, and I'm then going to have the 8i on the bottom, so I'm going to get 6i sine theta minus 2i sine 3 theta, and that's all over 8i. The i's will go, and in fact so will a factor of 2, which is just going to give me 3 sine theta minus sine 3 theta all over 4. And again, there's that tidied up for you. Just a word or two of explanation. We've used this to help us with that expression here, and in fact we've used that again down here to get these two in terms of sine 3 theta and sine theta. And when you work on through, when you get down to the bottom, you get that result. So we've seen that we can express coses or sines of multiple angles in terms of powers of cos or sine, and now that we can express powers of cos or sine in terms of multiple angles. And both techniques turn out to be very useful. De Moivre's theorem. That was the final video in this sequence, Complex Numbers 4, De Moivre's theorem.